You've gone through now the pain of computing the determinant of A minus lambda I here for this 3x3 matrix and perhaps made mistakes. I made mistakes my first time. The most common kind of mistakes are sign errors. So you do your very best to ignore, don't ignore them, try to fix them. It's most typical to expand about the first row, but you can find determinants by expanding about other rows or other columns. We didn't really talk about that, but it is advantageous if you've got zeros in a matrix to expand about rows or columns with zeros in them. But it is tricky because you'll also have to change how you do the alternating signs. Like if you expand about the first row like this, you do plus, minus, plus. If you expanded about the second row, you do minus, plus, minus. I never really talked about that, but that's something to be aware of if you ever look into determinants anymore in your life beyond this. But anyway, so we take the upper left corner, 3 minus lambda, and multiply times the determinant of this 2x2 submatrix. The absolute value signs really do not mean absolute value here. They mean take the determinant, which could be negative in general, so don't misunderstand that. Then the next number is a 1, but you got to alternate the sign to a -1 times the determinant of the submatrix formed by these things, crossing off that row and that column. Then +1, the last entry, times the determinant of this submatrix. And here are the details of my calculations. I made a couple sign errors the first time I tried. When I was expanding this one, for example, for some reason, my brain thought that was a -5 instead of a +5 when I expanded that. And I think I also made a sign error with one of these, but I did ultimately get it right now. I was checking my answers with Mathematica as I went. And I got this for the characteristic polynomial. A 2x2 matrix generates a quadratic second degree characteristic polynomial. A 3x3 will have a cubic characteristic polynomial. I did say there is a formula for solving any cubic. It's really more of an algorithm, but it's really, really complicated, so we don't really teach it. So instead, we hope that we're lucky and it's easy to factor, and we can guess our factorization by perhaps graphing. And if you do graph this cubic as a function of lambda, you get some graph, a graph that looks about like this. And lo and behold, you check it, 1, 2, and 3 are roots. Those are the eigenvalues, and that's going to mean you're going to be able to factor this as, well, there's a negative sign out in front, you can factor that out. Negative lambda -1, lambda -2, lambda -3. You're hoping that's true. The graph is no guarantee that the roots truly are 1, 2, and 3. Maybe they're just really, really close to 1, 2, and 3, but not exactly. So you really should check it by expansion. So this is a check here. Leave the negative sign out there. I'll multiply these two first. Get lambda squared -3 lambda plus 2. And then multiply this trinomial times the binomial. Just take it term by term with the second one here. Lambda times each of these gives lambda cubed -3 lambda squared plus 2 lambda. And then -3 times each of these terms gives -3 lambda squared plus 9 lambda -6. Distribute the minus sign through, combine like terms. We got a -6 lambda squared. Then with the negative sign there becomes a positive 6 lambda squared. And then here we have an 11 lambda with a negative sign becomes a -11 lambda. And then a -6 becomes a +6. And we have checked that we got the same thing here. Okay, so that is a worthwhile thing to do if you actually had to do this by hand to double check that this works. I won't do it, but if you're interested, you can try to use the fact that lambda -1 is a factor of this to use long division of polynomials, or maybe synthetic division if you've ever done that, to try to find the other ones. I won't go into details about that. If you've ever heard of that, that's something that can be done though. So the eigenvalues are 1, 2, and 3. 1, 2, and 3. All positive real numbers. That does mean the origin, well, none of them are 0 and the determinant of A is non-zero. The origin is the only equilibrium point in a 3-dimensional phase space. And these all being positive real numbers means it's a source, just like in the two-dimensional case. So solutions move away from the origin. Are there straight line solutions? Yeah, there are, because they're going to be real eigenvectors. Now we use technology to find them. There's my matrix A. I'll just go ahead and just do eigensystem right away. This output is telling you the eigenvalues are 3, 2, and 1. An eigenvector corresponding to the eigenvalue 3 is this vector, 0, negative 1, 1, which you would write as a column vector. An eigenvector corresponding to the eigenvalue 2 would be this one, negative 1, 1, 0, write it as a column vector. And for the eigenvalue 1, an eigenvector is 1, negative 3, 1. Those three vectors are linearly independent. How could you prove that? I'm going to go ahead and call the matrix P here right away. I'll put these vectors in the columns of the matrix. Okay, so I'm going to look at the first component of each vector first here. Now I'm looking at the second components. Now I'm looking at the third. That is a matrix that is invertible. Its determinant happens to be 1. That's a coincidence that it's 1. That's enough to say those three vectors as column vectors are linearly independent. They form a basis for R3. And you can therefore use them to create this matrix P to do a change of coordinates, which we will come back to, but also use them to find the general solution and solve initial value problems. Any scalar multiples of those would work as well, right? There are things called eigenspaces. The eigenspace for the eigenvalue 3 is a line to the origin in 3 dimensions parallel to that vector. I won't take the time to draw it, but you could try. The eigenspace for the eigenvalue 2 is the line to the origin parallel to this vector. And the eigenspace for the eigenvalue 1 is the line to the origin parallel to that one. When you have distinct real eigenvalues, you'll have linearly independent eigenvectors, and the P matrix will be invertible and A will be diagonalizable. Come back to that, but let's finish what I asked you to do. So your general solution for the differential equation, dy dt equals ay, general solution, I'll just use the book's notation, not bother writing a phi here, is k1 e to the, let's see, I guess in Mathematica we did the eigenvalues in the order 3, 2, 1, didn't we? Yeah, that's because that's the way Mathematica output was. So I'll use the eigenvalue 3 first, and its corresponding eigenvector, 0, negative 1, 1. And then k2 e to the 2t times its corresponding eigenvector, negative 1, 1, 0. And then k3 e to the t times 1, negative 3, 1. The order here doesn't matter. You could rearrange the order of these things. I just went with Mathematica's order. And again, any non-zero scalar multiples of these things would work as well. There are infinitely many general solutions. But the unique solution of any initial value problem is unique. The solution of any initial value problem is unique. Depending on how you write the general solution, the case could be different when you solve the initial value problem. But in the end, when you simplify, you should get the same answer. If you and your friend write two different general solutions that are valid, and you solve the same initial value problem, when simplified, it should be the same answer in the end. Now let's go ahead and solve the initial value problem. With that initial condition there, 4, negative 7, 3. By hand, y of 0. You know, e to the 0 is 1, that's nice. It's just k1, 0, negative 1, 1, plus k2, negative 1, 1, 0, plus k3, 1, negative 3, 1. I could think of this as the matrix P. This is not a bad thing to do. the matrix P that I entered into Mathematica times the unknown vector K1, K2, K3. I want to set that equal to 4, -7, 3 and solve for K1, K2, and K3. I could take the inverse of the matrix P if I wanted to, and you probably didn't do that. You probably got your calculator out and did row operations or did row reduce on Mathematica. Let's see if we get the same thing. Either way here. So I did enter my matrix P here. I could do the inverse of P times the initial condition vector, 4, -7, 3 to get K1, K2, and K3, 3, -4, 0. Did you get that? You could also do your row reduction on an augmented matrix. 0, -1, 1, 4, -1, 1, -3, -7, 1, 0, 1, 3. Yep. K1 is 3, K2 is -4, K3 is 0. Plug in 3 there. The coefficient of e to the 3t, if you use that eigenvector at least, is 3. Plug in -4 there. If you use this eigenvector, that's a -4. And this one's 0. That's the solution of the initial value problem. It's a parametric curve in 3-dimensional space. You could try to get Mathematica can try to draw it with something called parametric plot 3D. We won't take the time for that. But let's also spend a little time talking about coordinate changes. This will also help for the homework. So this is my matrix P, again, that can diagonalize A. Why? Because the columns are the eigenvectors, linearly independent, P inverse exists. If I compute the inverse of P times A, use a period, times P itself, that should be a diagonal matrix. If you want to find the diagonal matrix by multiplication, put P inverse first. There it is, 3, 2, 1. Okay. What does that mean? What's the significance of that? If we wrote our solution of a generic initial value problem, now I'll go use the capital Phi notation. We know by the beautiful generalization that this is e to the TA times y naught. And what else have I told you? If A is diagonalizable, again, that means the diagonal matrix D is P inverse AP. That's equivalent to saying A equals PD P inverse. How do you get from here to here? You just do some multiplication. On the left side of this equation, multiply by P. Then you get P times P inverse, which is the identity. You get an AP over here, and you also got to multiply it on the left. You get a PD here. And then you also multiply on the right by P inverse. And you swap the sides here. You get A as PD P inverse. And because of that, I've improved this, but because of that, that ends up meaning that e to the TA, the matrix exponential, is an analogous kind of equation. P e to the TD times P inverse times y naught. So we could confirm the solution of the initial value problem with this formula. Let's do that quick. Well, I guess I never wrote it down by hand, or I said it. It's, the K1, K2, K3 are fairly simple. It should turn out fairly simple. So what am I going to do again? I'm going to do this calculation right there. Matrix form. Just formats the output as a matrix. P times the matrix exponential of e to the TD. I could use matrix X, but just for emphasis, let me actually type in the matrix exponential. E to the 3t, 0, 0, 0, e to the 2t, 0, 0, 0, e to the t. That works because D is diagonal. In general, the matrix exponential is difficult to compute, but when D is diagonal, its matrix exponential is easy. Inverse of P times the initial condition vector. That's my why not. Simplify. Why does it do that? Expand, multiply through. Okay, you see the 4s and the 3s, right? Corresponding to the 3 and the 4 that we got here. And you don't see any e to the t's. The coefficient for e to the t term was 0. K1 was 3. That's a 3. You don't see a 3 in the first component. You see a -3 right here, corresponding to 3 times -1. A +3 right here, corresponding to 3 times 1. And the K2 was -4. -4 times -1 is +4. -4 times +1 is -4. And -4 times 0 is 0. You don't see it. And e to the 2t term down here. Okay, pretty cool. I like it at least. Something else comes up on the homework and the lectures that's worth mentioning here before we briefly talk about the trace determinant problem. To really get into the change of coordinates idea. We talked about change of coordinates. We've talked about coordinate vectors and that kind of thing. That's coming up, if you haven't watched it yet, in lecture, whatever it is, 26C or something like that. There's 3 parts to it. Part C. We don't bother with the coordinate vector notation where you put the square brackets around the basis. We use a new letter, a new variable. Essentially, you let a new variable vector u be defined by this equation, and this is the way I remember it. Y equals pu. I remember it's that one instead of y equals p inverse u because, well, pu. And that's equivalent to u equals p inverse y. So effectively, y is the original coordinate system. For a two-dimensional system, that'd be the ordinary xy axes. It's the coordinate vector with respect to the standard basis. And u is going to be a coordinate vector for the same points with respect to a new coordinate system, like a skewed coordinate system. And what you want to be able to do is you want to be able to write your solution using these ideas. How? Well, it's related to how you think about the differential equation. The original differential equation is dy dt equals ay. What's the corresponding differential equation for u? Use this equation. Du dt, differentiate both sides of this equation, is, well, P inverse is a constant matrix, so it just stays as is. P inverse times dy dt. But what's dy dt? Ay. But what's y? Pu. Maybe I should write one more step in here. Y is Pu. And what's P inverse AP? It's D, the diagonal matrix. This is an abstract verification of the fact that with respect to the new coordinate system, the system is completely decoupled because D is a diagonal matrix. It's easy to solve. You can solve it by inspection. You can write down the matrix exponential by inspection. It's an abstract verification that what you're really doing when you find eigenvalues and eigenvectors is you're changing to a new coordinate system in which the system is easy to solve. That's what you're really doing down deep. But the textbook doesn't talk about that. But since we're talking about so much linear algebra, this is a combo course that's worth talking about for us. All right. You can also talk about the flow, well, the solutions for this system being capital phi sub y naught of t. For this system, got to use a different Greek letter. How about psi? Oh, is that sacrilege? Isn't psi quantum mechanics? Not here, it's not. Okay. I'm not very good at making psis, so sorry about that. Solution, they both have formulas that are the beautiful generalization. But those formulas are related by the coordinate change. I'll let you learn about that in the lecture or the PowerPoint.